We know that the Legendre symbol A by P is defined only for primes which are greater than 2. That is, the Legendre symbol is defined for only the odd primes P. Now, we are going to define Jacobi symbol, which is in fact a generalization of Legendre symbol. Here we assume that A is an integer and N is a positive odd integer. We let N equal to P1 raised to alpha 1, P2 raised to alpha 2 and so on, PR raised to alpha R be the prime factorization of N. Then we can define the Jacobi symbol A by N as the product of Legendre symbols for the prime factors of N. That is, we can define Jacobi symbol A by N as the product Legendre symbol A by P1 raised to alpha 1, A by P2 raised to alpha 2 and so on, A by PR raised to alpha R. Let us note that if Jacobi symbol A by N is equal to 1, then it is not necessarily true that A is S square modulo N. But we know that if we are considering Legendre symbol A by P, then A by P equal to 1 if and only if A is a square modulo the prime P. But this is not applicable for Jacobi symbol. For example, if we consider Jacobi symbol 2 by 15, then we can express it as 2 by 5 into Legendre symbol 2 by 3 using the definition of Jacobi symbol. And this is equal to minus 1 raised to 5 square minus 1 by 8 is the value of Legendre symbol 2 by 5. Similarly, the value of Legendre symbol 2 by 3 is minus 1 raised to 3 square minus 1 by 8, which will be minus 1 raised to an odd number 3 into minus 1 raised to odd number. So, the product will be plus 1. But we can easily verify that there is no integer x in the set 1 to etc. 14 such that x square is congruent to 2 modulo 15. That is, 2 is not a square modulo 15 in spite of the fact that Jacobi symbol 2 by 15 is equal to plus 1. Now, let us consider a few properties of Legendre symbols. First one is a proposition which states that for any positive odd integer n, we have Jacobi symbol 2 by n is equal to minus 1 raised to n square minus 1 by 8 proof. We can see that this property is similar to that of the Legendre symbol. That is, we have already proved that Legendre symbol 2 by P, where P is an odd prime, is equal to minus 1 raised to P square minus 1 by 8 for an odd prime P. That is, P is greater than 2. But we need to show this result for any positive odd integer n. Now, let us label this function minus 1 raised to n square minus 1 by 8 as f of n. Then we can show that f of n1 n2 is equal to f of n1 into f of n2 for any two odd integers n1 and n2. Proof of the claim. We know that as n1 and n2 are odd, n1 plus 1 into n1 minus 1 will be the product of two even numbers, and one of them will be a multiple of 4 and the other will be a multiple of 2. So this product will be a multiple of 8. That is 8 will divide n1 square minus 1. That is the product n1 plus 1 into n1 minus 1. Similarly, 8 will divide n2 square minus 1 also. Therefore, n1 square minus 1 by 8 and n2 square minus 1 by 8 are all integers. Now, we can write f of n1 n2 as minus 1 raised to n1 square into n2 square minus 1 divided by 8. Here, in the numerator, we can add and subtract a term, say n1 square. Then we can express the same value as n1 square into n2 square minus n1 square plus n1 square minus 1 upon 8. This can be expressed as n1 square into n2 square minus 1 by 8 by taking only the first two terms and grouping them together. And we have taken this n1 square as a common factor also into minus 1 raised to remaining terms, which will be n1 square minus 1 divided by 8. So, this will be equal to minus 1 raised to n2 square minus 1 by 8 whole raised to n1 square into minus 1 raised to n1 square minus 1 by 8. The quantity in the square bracket, that is minus 1 raised to n2 square minus 1 by 8, is in fact f of n2. f of n2 raised to n1 square into the second quantity will be f of n1. Thus we have obtained that f of n1 n2 is equal to f of n2 raised to n1 square into f of n1. Here we know that n1 is odd, so n1 square will be odd. So f of n2 raised to an odd number, where we know that f of n2 is either plus 1 or minus 1. In both cases, f of n2 raised to an odd number will be f of n2 itself. So here we can write f of n2 into this quantity, which is f of n1. So we have obtained that f of n1 into n2 is equal to f of n1 into f of n2 as required in the claim. Therefore, for odd integer n, we can express f of n as f of p1 raised to alpha 1, p2 raised to alpha 2, etc. pr raised to alpha r, which is the prime factorization of n, and it will contain only odd primes since n is odd. So each of these primes p1, p2, etc. pr are odd primes. And now this can be expressed as f of p1 raised to alpha 1 into f of p2 raised to alpha 2 into etc. f of pr raised to alpha r, using the multiplicative property we proved above. And we know that f of p1 is equal to minus 1 raised to p1 square minus 1 divided by 8, and that is in fact the Legendre symbol 2 by p1, as we have proved earlier for Legendre symbols. Hence, we can substitute 2 by P1 for f of P1. So, we get 2 by P1 raised to alpha 1. Similarly, f of P2 can be replaced with Legendre symbol 2 by P2. 2 by P2 raised to alpha 2 and so on. F of PR will be 2 by PR raised to alpha R, and this is in fact 2 by P1 raised to alpha 1, P2 raised to alpha 2 and so on, PR raised to alpha R using the definition of Jacobi symbol. So this is nothing but 2 by n. Thus we have proved that f of n is equal to 2 by n. Since f of n is minus 1 raised to n square minus 1 by 8, we have showed that minus 1 raised to n square minus 1 by 8 is in fact equal to Jacobi symbol 2 by n as required in the statement of our proposition. Thus, the proof of our proposition is complete. The next is a proposition which is similar to the quadratic reciprocity law for Legendre symbols. It states that for any two positive odd integers m and n, we have Jacobi symbol m by n is equal to minus 1 raised to m minus 1 into n minus 1 by 4 into Jacobi symbol n by m. For the proof, let us consider the first case when m and n have a common factor. Then what will happen to both Jacobi symbol m by n and Jacobi symbol n by m? We can see that if both m and n have a common factor, then there will exist some prime, say pi, such that p will divide both m and n. Then, since pi divides m, we will have m by pi, the Legendre symbol will be equal to 0 using the definition of Legendre symbol. And this will imply that Jacobi symbol m by n is equal to 0. Since Jacobi symbol m by n will be the product of all such Legendre symbols. So m by n will be equal to 0. Similarly, since n by pi, Legendre symbol will be equal to 0 as pi divides n, we will also get Jacobi symbol n by n equal to 0. Thus, we have in case 1 both Jacobi symbol m by n and Jacobi symbol n by m are 0. In this case, this equation will be satisfied. Now, let us move on to more general case in which m and n do not have a common divisor. That is, if GCD of m and n is equal to 1. Now, we write both m and n as the products of primes. We write m is equal to p1 into p2 into etc. say pr, and similarly let n be the product of primes q1, q2 etc. qs. Here the p's and q's may include repetitions if m or n has a square factor. Now, m by n, Jacobi symbol m by n can be expressed as m by q1, q2 etc. qs, and that will be equal to the product m by q1, m by q2 etc. m by qs using the definition of Jacobi symbol, and this is equal to, here the Legendre symbol m by q1 can be expanded as p1 by q1 into p2 by q1 into etc. pr by q1 using the properties of Legendre symbols. Similarly, the Legendre symbol m by q2 can be expanded as p1 by q2 into p2 by q2 etc. pr by q2 and so on. M by qs can be expanded as the Legendre symbol p1 by qs into etc. pr by qs. Thus, Jacobi symbol m by n can be expressed as the product of Legendre symbols of the form pi by qj, where I varies from 1 to r and j varies from 1 to s. Let this be equation 1. Now, using similar process, we can express Jacobi symbol n by m as a product over I and j, qj by pi. And let us label this as equation 2. If we want to relate these Jacobi symbols m by n and n by m, we can apply quadratic reciprocity law to the right side of, say, equation 1. That is, we need to apply quadratic reciprocity law to these Legendre symbols pi by qj. When we apply quadratic reciprocity law, we know that Legendre symbol pi by qj is equal to minus of qj by pi when both pi and qj are congruent to 3 modulo 4, and pi by qj will be equal to qj by pi in all other cases. We know that there will be r into s Legendre symbols in this product, since I varies from 1 to r and j varies from 1 to s. There will be r into s terms, r into s factors in this product. So we will need to apply r into s times, rs times the quadratic reciprocity law in this product. Thus, in converting the RHS of 1 to RHS of 2, we must apply the quadratic reciprocity law for Legendre symbol r into s times. Then the number of minus ones we get will be equal to the number of times both pi and qj are congruent to 3 modulo 4. We know that only when both pi and qj are congruent to 3 modulo 4, we will get a minus 1 when we apply quadratic reciprocity law to a particular Legendre symbol pi by qj. Thus, the number of minus ones we get can be expressed as the number of pi's congruent to 3 modulo 4 into number of qj's congruent to 3 modulo 4, where pi's are those primes which are in the factorization of m and qj's are from the factorization of n. Thus, Jacobi symbol m by n is equal to Jacobi symbol n by m unless there is an odd number of primes which are congruent to 3 modulo 4 in both factorizations. That is, the number of minus ones will be odd only when both of these numbers, number of pi's and number of qj's satisfying this property, are odd. That is, unless there is an odd number of primes congruent to 3 modulo 4, we will be getting m by n is equal to n by m. And in this case, that is, when there is an odd number of primes satisfying this condition, we will be getting odd number of minus ones, and then Jacobi symbol m by n will be equal to minus of Jacobi symbol n by m. But we know that a product of odd primes such as m or n is congruent to 3 modulo 4 if and only if it contains an odd number of primes which are congruent to 3 modulo 4. That is because if we write m is equal to p1, p2, etc. pr, then we can see that every prime is congruent to 1 or 3 modulo 4, and m is equal to, a prime will be either a multiple of 4 plus 1, or there may be prime divisors which are multiple of 4 plus 3 in the factorization. So the product m will be something like this. Here there may be a few primes which are congruent to 3. So there may be a few factors like this, and there may be a few primes which are congruent to 1. So there may be a few factors like m multiple of 4 plus 1 in the factorization of m. The product, if we multiply all these factors, all the terms except the term we obtain by multiplying these numbers 1 into 3 into this, all these terms, we can express the product as 3 raised to k, where k denotes number of primes in the factorization which are congruent to 3 modulo 4, and all the other terms in the product will be multiple of 4. And we can see that 3 raised to an even number, here we are trying to check whether 3 raised to k will be a multiple of 4, or will it be congruent to 1, or will it be congruent to 3. So let us check the case when k is even. Then we can express the exponent as, say, 2l. Then we can express this as 9 raised to l, and 9 is in fact a multiple of 4 plus 1 raised to l. When we expand this using binomial theorem, we can see that all the terms other than the last term will be containing multiple of 4. And the last term will be 1 raised to l, which is 1 itself. So in this case, that is when k is even, small m will be, this product will be multiple of 4 plus 1. Since 3 raised to k is congruent to 1 in this case, and so m is congruent to 1 modulo 4 in this case. And when k is odd, then 3 raised to odd can be expressed as 3 raised to some 2l plus 1, and this can be expressed as 3 into 3 raised to 2l, and that will be 3 into 9 raised to 12. So 3 into, we already know that 9 raised to 12, that number is of the form multiple of 4 plus 1, and this will be equal to multiple of 4 plus 3 into 1 is 3. Hence, in this case, 3 raised to k is congruent to 3. So, small m will be congruent to 3 modulo 4. Thus, we can see that small m, the number, is congruent to 1 modulo 4 if the number of primes which are congruent to 3 modulo 4 is even, and m is congruent to 3 modulo 4 when the number of primes congruent to 3 modulo 4 is odd. This conclusion is stated here. That is, a product of odd primes is congruent to 3 modulo 4 if and only if it contains an odd number of primes. We denoted this number as k. If k is equal to odd. So, m by n is equal to plus n by m unless both m and n are congruent to 3 modulo 4. And if both m and n are congruent to 3 modulo 4, then Jacobi symbol m by n will be equal to minus of Jacobi symbol n by m. Thus, we have obtained the result that m by n is equal to minus 1 raised to n minus 1 into m minus 1 by 4 into Jacobi symbol n by m.